So in the last class, we discussed the idea of how Turing machine came about, the mathematical history behind it, what is the motivation behind it, right? So yeah, silence. So last few classes, that's what we discussed. Okay. So Turing machine and lambda calculus, they were invented independently, but both of them were found to be equally powerful. Okay. And whatever can be done on this computer, it can be done on a Turing machine. And if something cannot be done on a Turing machine, it cannot be done on our computers as well. Okay. So the idea of Turing machine seems actually quite simplistic. It is, I mentioned already, it's an infinite tape with many cells. Each cell has some symbol. You have a read-write head which points to some particular cell. It can just read the content of that cell, or it can overwrite the content of that cell and move left or right. And this process continues. This is what a Turing machine is, to put it simply. That's all. Later, there is something called cellular automaton. It is presented in the form of sort of game. It's called Conway's Game of Life. You can, so that's what I'm going to show. So this is also as powerful as a Turing machine. Okay, so this is nothing but a grid of cells where each cell is either white or black. It means it is either alive or dead. And based on some rules, some 3-4 rules are there. Depending on how many neighbors a cell has, it will stay alive or it will die, or a new cell is born. That's all. So based on these simple rules, you will see what can be done. Okay, what kind of things one can achieve using these simple rules. Okay, so let's just check it. So all this is happening based on those 4 rules. So the states of the cells are changing. That's all. Okay. So the idea is, even though the rules might look pretty simple, what they can generate is pretty complex, and the rules themselves may not seem much meaningful, but the output acquires some meaning. It is similar to like this physical universe, or even if you take a materialist stand that everything is made up of matter, then even the societal interactions, our emotions, our feelings, everything somehow reduces to atomic interactions. Atomic interactions are simple, they have few rules. But how these meaningless syntactic atomic interactions give rise to such rich meanings, that is a very complex thing, right? That is an enigma. Okay, first of all, that is if you take a materialist stance that everything is made up of matter, you can also take a dualist stance that mind is separate from matter. You can take a pluralist stance that there are more things than mind and matter. So any stance you can take, but the point is the basic rules of a system, although they may look simple, the output can be very complex. So that's exactly the case with Turing machine also. That's the case with cellular automata also. Even in Turing machine, like I said, it's a very simple mechanism. You have a tape, you have some symbols, you have a read-write head which can read a symbol or override that symbol with some other symbol and then move left or right. This process continues. That's all. So whatever complex things we are able to do using our machines, supercomputers, this, that, all these things can be done on the Turing tape. It's just that it may take much more time, but it can be done. So this cellular automaton, one of the models which it showed is also like model of a Turing machine. And also Turing machine can simulate itself the way a 3D printer can print a 3D printer. Okay, so these things are there, and this is all related to grammars. So this is a grammar. These four rules which you saw, like if it has 2 or 3 neighbors, a cell lives. If it has less than 2 neighbors, it dies. Or if it has more than 3 neighbors, also it dies. And if it has exactly 3 neighbors, a dead cell becomes alive. These four rules, that's all. Given these four rules, by changing the initial conditions, by giving different initial states, you get entirely different simulations. Okay, this is a grammar. So grammars are extremely powerful. They give rise to a finite set of rules. So grammar is nothing but this set of rules which we saw. We will also in this course look at different grammars. Turing machine is also based on some grammars. It's a class of grammars. Below that, we have other classes. We have regular grammars, we have context-free grammars, context-sensitive grammars, and all that. So each class of grammars generates some kind of sentences. Okay, but they're extremely rich. And so finite set of rules can give rise to potentially infinite sentences. Even our languages have grammars, right? Natural languages which we speak, we study grammar in school, right? That grammar is also finite, but we can generate potentially infinite set of sentences with the finite set of rules we have. Another interesting thing about language is, you see, how do we get the meaning of a sentence? What is the procedure? One way is we sort of have a database of all possible sentences that can be spoken of by anyone in this universe. And whenever someone speaks that sentence, we go to this database, we map the spoken sentence with the sentence in the database and extract the meaning from the database. That is one way. But none of us would think that is how it happens, right? Because we cannot have such a database because it's potentially infinite. The interesting thing is, every time someone speaks a sentence, it is almost always a new sentence. But still you're able to understand it easily. It's not like, okay, I heard this sentence earlier, that's why I'm able to understand it now. I didn't hear this sentence earlier, I don't know what its meaning is. We don't say that, right? Everything you read or you hear, it's almost always you are hearing or reading that particular thing in that particular phrasing you are hearing or reading for the first time, but still you are able to understand it. How? That is because we are beings of grammar. We are grammatical beings. We have this innate ability to decode the grammar of something, to recognize patterns in some data, be it linguistic data, visual data, whatever it is. We can recognize patterns. We are pattern recognition machines. That is exactly what machine learning tries to do. Machine learning is basically a pattern recognition exercise. So when we say a machine is learning something, what is it learning? You throw some data at it. It is trying to learn the patterns from that. It is trying to extract some meaningful information from that. What is meaningful? The patterns, the features. So our innate ability of recognizing patterns within a text or a picture or music, whatever it is, that it's in fact, even with respect to someone's behavior, actually grammar is applicable not just to language or visuals. It is applicable to almost anything and everything in this universe. Even a person's behavior has a grammar. It has a pattern. That's why we are able to predict how a person is going to behave in a particular situation, or we can guess how some person behaved in a particular situation. It is because we sort of get the pattern of that person's behavior. We get the pattern of a country's culture or a community. So these are all patterns. Some patterns are complex, some patterns are simple, but nonetheless, there are patterns everywhere. And we try to understand these patterns. And these patterns are nothing but the grammar of that particular data set. So understanding the pattern of some data is nothing but understanding its grammar. And this theory, this course deals with the theory of grammars. You will look at different kinds of grammars and their counterparts, which are parsers. We will look at different levels of grammars and parsers, but this is what the course is about. But don't think it is limited only to computer science grammars. The idea of grammar is much wider than just computer science. Even to art, you can apply. Someone's painting has a grammar. Looking at a painting, you can say, okay, this looks like Picasso's painting. This looks like Da Vinci's painting. How are you able to say that? Because there is a pattern for Picasso's paintings. There is a pattern for Da Vinci's paintings. That is the grammar. Okay, so there is grammar for language, there is grammar for paintings, there is grammar for art, there is grammar for emotions, there is grammar for someone's behavior, there is grammar for a culture. Everything has a grammar. All right. An interesting thing is, say, at least if you take the example of language, how do I understand the meaning of a sentence? There are different schools with respect to this question of how does a human understand the meaning of a sentence, right? There are multiple ways. One is, like, even before that, a prerequisite, or it begs the question, what is the basic unit of meaning? Is it a word or a sentence? What do you people think? How many of you think word is the basic unit of meaning? How many of you think sentence is the basic unit of meaning?
Probably neither, sir.
Okay. Then what is the basic unit of meaning?
The way things are connected.
Somewhere meaning should have some building blocks, right?
The connection itself is the meaning.
Connection itself is the meaning. No, in language,
We can have the blocks, but the blocks by themselves might not have any meaning. For example, when we say a word is composed of phonemes, right? The
phonemes don't have, fine, but word has, right?
Because the phonemes are connected in a particular way. Connection is what gives it the meaning. Connection and regularity.
I can connect phonemes in an irregular way also.
A specific sort of connection gives meaning.
Yeah, but why that specific sort of connection only has meaning, not some other specific sort of connection?
Because we understand, we detect certain things and don't detect certain.
Whatever is the format of connection, the point is somewhere meaning should start. It may not start at the level of phonemes. It may not start at the level of word, as you are saying. Does it at least start at the level of sentence, or it does not start there also? Or it is not there at all? Somewhere it should be there, no? Somewhere it should start. There should be a starting point. Sound, but like he said, every sound need not have a meaning. Like music, you can have music without any meaning, pure sound, without lyrics, just sound. It can be noise, it can be music, but meaning comes when you have some words, not just sounds, right? So anyway, let's not spend too much time on this. The point is, there are two schools. One school says word is the basic unit of meaning. Another school says sentence is the basic unit of meaning. How can sentence be the basic unit of meaning? For instance, if I say if I say door, I know door means door, right? So I can say this word is the basic unit of meaning. No, the point is, in experience, even if I tell you, say the word door, you don't take it just as door. Okay, he said door. That's it. You don't think like that, right? You will fill in by you will fill in various ways. Is he asking me to look at the door, or is he asking me to close the door? Is he asking me to open the door? Is he saying someone is standing at the door? He is saying something. So even though a word is told to you, you always make it into a sentence. Without that, it doesn't make any sense to you. You know what a door is, but that is not really so-called meaningful. That doesn't have any context. You fill in the context. Meaning comes when you have the context, like he said, some relation, some context, a particular way of arrangement. All these things are necessary for you to get some meaning. Okay. So some say sentence is the basic unit of meaning. Some say word is the basic unit of meaning. These are different schools. In Indian philosophy, there are many schools. Now, the next question is, okay, how do I get the meaning when I listen to a sentence? Is it done incrementally, or is it done in a go, instantly? If it is done incrementally, is it the case that, okay, I am hearing word by word, suppose there is a sentence with 10 words. As I am hearing each word, the meaning is incrementally being constructed in my mind. Is that the case? Or after I hear the entire sentence, at the end of the sentence, the meaning suddenly sprouts? Both theories are there. Again, these are different schools. Okay. Each one has its own arguments and counter arguments. But what I'm trying to say is, people have dissected, people have analyzed human experience so much that all these questions were raised and elaborate theories were given related to these things. Okay. So anyway, so what I wanted to say is, grammars are there everywhere, and not only in computer science, they are there everywhere. Grammars are nothing but the patterns which we recognize in a particular data that is given to us. Whatever kind of data it is, visual, audio, sensual, textual, it can be someone's behavior, all kinds of data. They have a pattern, and we try to recognize that pattern. That's all. I don't know how many of you watched this movie, A Beautiful Mind. So what is his ability? He somehow sees patterns in numbers. He is not like any mathematician. It's like it's basically like a biography of John Nash, a Nobel Prize winner. Nash equilibrium is something very popular. So it's about him. He is an eccentric person, not a normal person. He looks at things differently, and he can see patterns in numbers. Somehow instinctively, he is able to do that. So it's an excellent movie. You have to watch it. So you see, movies can also be very useful. They're not always recreational. They are also informational. They are educative. As an experience, also movies can be analyzed to a great extent. Anyway, so there are some good films which you have to watch. Like I said last time, Lucia, Kannada film. This one, Beautiful Mind. You have to watch these things. Okay. So some people can recognize patterns better than others. All right. So it's an intuitive exercise. Even we will see many examples of grammars. How to build a grammar? There is no mechanical automatic way. You somehow have to intuit. There is some kind of creativity involved in coming up with a grammar. Okay. So far the idea is to just give you the motivation behind Turing machine, the background behind Turing machine, the mathematical background and the history. We will revisit Turing machine in the later half of the course, but I just wanted to set the base for this course, what this course is about, and this has a lot to do with mathematics. So that's all. So now we will get into the topics. We will get into textbook content. So far, what we covered is not in the textbook. It's not in one textbook. It is various places. So you won't find any one particular resource. That's why I don't give you one resource. Look at the lecture notes. Any of doubts, I will also upload those lecture videos which I recorded soon. I will do so. Okay. So in the last in most of the earlier lectures, this course has uh, so the difference structure is like this. Completely depends on computing. So we will cover them in order. We'll first cover automata theory, and then complex theory. Okay? So we'll cover automata theory, and what's automata theory? Like I mentioned, it will mathematical models. Okay. So so what is the definition of a Turing machine? How do you define a Turing machine and all that? Before we discuss mathematical models, but for that we need to set a base, a mathematical base. So we need to read some of the mathematical concepts which you already know, which were covered in discrete maths course, but we will quickly revisit some of them from the perspective of this course. All right. So let's start. So we will start with set theory. Like I mentioned earlier, set theory is the foundation of entire mathematics. Whatever discipline, sub-discipline in mathematics you can take, it can be reduced to set theory, be it algebra, geometry, trigonometry, calculus, arithmetic, whatever you take, it can be reduced to sets. So set theory is so fundamental. Okay. So we have to look at set theory even for this, for computer science also set theory and discrete maths is very useful and very important. That's why you have that course as well, discrete maths course. Okay. So we all know what a set is, a well-defined collection of objects. And there are two ways of representing a set. What are those? You know already. What are the two ways in which you can represent a set? Not Venn diagram. Roster notation and set builder notation. This set builder notation is also called intentional notation. And roster notation is also called extensional notation. Okay, so let's take an example. Suppose there is a set of all x's such that x is a positive integer and x mod 3 is equal to 0 and x is less than 10. So in roster notation, how does it look? Roster notation means what? Hmm? Yes. So the element which is contained forward. So it's written roster notation. It is nothing but the entire list of elements sort of given out explicitly. Okay, it does not tell us what is the characteristic thread among all these elements. There is one characteristic thread, but it does not tell it out explicitly. Okay? So, what is the pattern among all these elements? Is a set builder notation. So, set builder notation is a description of the pattern of all the elements listed in roster notation. So, if you want to use set builder notation, if you want to list out the element, use roster notation. Okay. So we usually write set notation like this: A equal to set of all x's such that P of x is true, where A is a set of all those x's for which the predicate P of x is called the predicate. Okay, so this is set builder notation. And then cardinality of a set. What is cardinality of a set? Hmm? What is cardinality? Yeah, the size of a set or the number of elements in a set. Okay. Now let's look at some set operations. Let a equal to 1 comma 2 and b is 2 comma 3. So A union B, how do I write in set builder notation? X such that
belongs to A and X, or X belongs to
yeah. So we can write it as X is in A or X is in B. Okay. So for the above example, what is A union B? What is A union B? 1, 2, 3. So intersection B is X is in A and X is in B. Okay. And in the above example, A intersection B is 2. Okay. Then set difference. So here what should we write? X such that X belongs to B. Why so complicated? That's all. X is in A and not in B. So for the previous example, what is A minus B? 1. So Cartesian product A cross B is the set of A comma B such that A is in A and B is in B. Okay. So if you take an example of A as 1, 2, 3, P comma Q, then how many elements will be there in A cross B? 6, because A has 3 elements, B has 2 elements, A cross B will have 6 elements. In each pair, first element comes from A and the second element comes from B. Okay. reducible set by set. Right. So if A is 0, 1, so how many elements will be there in the power set of this? A has 2 elements. How many elements will be there in the power set? 4. So what are those from smallest to largest?
Null set,
Yeah, null set
singleton 0,
0,
singleton
1,
A,
and 0, 1. Okay, so this we all know as empty set or null set. And these both are singleton sets since they have only one element. Okay. Now there can be a cross product of not just 2 sets but even k sets. Okay. Now how does each element in this cross product look?
like here, A1, A2, A3, and so on till AK, where A1 belongs to A capital A1, set A1.
Right. So it will be a tuple with A1, A2, A3, and so on up to AK, such that AI belongs to capital AI, where 1 is less than or equal to I is less than or equal to K. Okay. And a set can have a cross product with itself. Okay, so we can write A cross A cross A and so on, say K times. This is represented as A power K. Okay, so one can speak of A square, A cube, etc. For a set, it means it is the cross product of the set A with itself. So if it is A power K, it means A cross A and so on, K times A. Okay. Done? All right. Next. Sequences and tuples. A sequence of objects is a list of objects in some order. sequence is designated by writing the list within parentheses. So for example, this is a sequence. Okay. Done. The order doesn't matter in a set, but in a sequence it does. So if we take the same sequence, it is not the same as say 21, 7, 57. Elements are same, but the order changed, so it's a different sequence. Okay. Similarly, so let me copy this. Repetition doesn't matter in a set, but in a sequence it does. Before that, let me take a set example also here. So if you take a set of these three elements, it is same even when you change their order. It is the same set. Okay. So here, okay, whereas it doesn't matter in a set, no matter how many times you repeat an element. So in a set, neither the order matters nor the number of times you repeat an element. Okay. Like sets, sequences can also be finite or infinite. Finite sequences are called tuples. A sequence with k elements is referred to as a k tuple. So for example, this is a 3 tuple. A tuple with only 2 elements that is a 2 tuple is also called an ordered pair. Okay, 2 more minutes. So what is the difference between a function and a relation? Anyone?
Function will cause certain things when a relation is just a correlation.
Function will call certain things. Cause. Okay. Any other answers? What is the difference between a function and a relation? Quickly. Huh? You did discrete maths course, right? Even in school, you would have studied this. What is the difference?
Function is a relation with additional condition imposed on it. Says that everything belonging to the set that it's set. Let's say a function is mapping A to B, then every element in A must be associated with an element in B. That is the additional condition imposed on a function which a relation does not have.
That's all?
Yes, actually.
Something more. So,
Well defined, it cannot, one thing in A cannot be two or multiple things in
yes.
That's
Yes. Yeah, there's no difference there between well-defined function and function. It will be a function only if it has one-to-one mapping or many-to-one mapping. It cannot have one-to-many. It cannot be a function at all. Okay, so a function is also a relation, but a function, is there a class? Yes. Okay. So a function can have one-to-one mapping or many-to-one mapping, but it cannot have one-to-many mapping. A relation can have, whereas a function cannot have. Okay. So anyway, we'll continue in the next class. I'm not taking attendance today because there is some problem with Juno. So.